Thank you very much for that introduction. I think confusingly we call it MrParse and Mr. Bump, so there's no consistency. So yes, I'll be talking about MrParse today. What we've developed MrParse to do is to try and aid in molecular replacement decision making. So to give you a quick overview of the talk, I'm going to split this into two parts. The first will be on MrParse now, a little bit of background about why we decided to develop it and how you might run it. The second part, which I think is perhaps more interesting, will be the areas that we're currently developing. And this will be the new motivation in the form of in silico model databases, and then answering some questions about these, such as whether the models are good enough for MR and how we can access these models. So there's quite a rich amount of information available about potential search models for molecular replacement, and bioinformatic predictions can be really useful to help us choose a good search model. It's my experience that this information tends to be scattered across the place. It's on loads of different web servers and loads of different local programs. What we want to do with MrParse is to try and collect all this information into one place. So on to running MrParse. Unfortunately, the first step in running MrParse is finding it. It's currently a little bit hidden in the CSP4i2 interface. Currently, it's under the validation and analysis tab, which makes a sort of sense as it is an analysis, but we want to migrate this to the bioinformatics tab later in the year because of it's a sort of step before molecular replacement. The requirements for running MrParse are a sequence, so a FASTA file, or in I2 lingo, AU contents. We use the sequence to try and identify potential search models using FUMA, although I think we might modify it to use HHPRED in due course. And an MTZ file, which we use to try and provide a little bit of information about your reflection data and also to calculate the eLLG. If you're running this on command line, you can also use a protein classification flag, and that will do some assessment of the sequence and give you information about the secondary structure, coiled coils, and transmembrane features. So when you run MrParse, you get a page up that looks a bit like this. It's an HTML page, just open in any browser. The first box I've highlighted in red here is your HKL info, and that gives you information about resolution, space group, whether it has non-crystallographic symmetry, twinning, or anisotropy. Then we have some homolog information. So we have two hyperlinks here, the first of which will go to the locally downloaded model. The second will go to the PDB, and then we also give information about the resolution at which the structure was solved. Then we have range, region, range, and length, which correspond with this visualization on the right-hand side. So each color represents a different region, and the range and length are sort of just visualized here. Then the final thing I want to talk about in this table is eLLG. So I think Ellie went into a little bit of detail about what eLLG is in the last talk, but essentially it's a phasor metric to try and give you an expected log likelihood gain by looking at the model and looking at the reflection data. Higher is generally better. In this case, it says 820, which is you'd expect to be superb. And finally, we have a sequence-based prediction. So I've got my secondary structure prediction here, coiled-coil prediction. This isn't a coiled-coil protein, so it's null and void really. And then transmembrane features, which are across. Now, if we had a look at this page as if we were trying to solve the structure, there are a few interesting things that we can look at. Resolution is about 3.4 angstrom, so you might be able to make some predictions about what programs will and won't work at this point. So automatic model building might be a bit difficult. Then if we look at the top homolog, well, I've already mentioned a very high eLLG. You'd predict that this one would work. It also covers the entire region of the protein. But let's say we tried that in molecular replacement and it failed. We might also look down the list and see this is actually probably a two-domain protein. There's these domains over here on the right, and then these domains on the left. That second entry is 99% sequence identity, so it's got a better sequence identity. It also has a really high eLLG. That would perhaps work better in case there may have been some sort of conformational change in the protein. Right, I'm going to move straight on to areas under development. So our new motivation has come from the fact that there are now protein model databases. These are models of a new kind, covariance-informed ab initio models that are now capable of addressing novel folds, and they're supplementing familiar databases of homology models. So to give some examples, there's Gremlin, pConsFam, and as we heard in Kelly's talk, EV coupling. So some of these models are now being made available directly at well-known databases like Interpro, PFAM, and Uniprot. But we need to know, are the models good enough for MR, and how can they be made easily accessible? Well, on that first question, are they good enough for MR? I'm going to talk about a little bit of work that we did at the tail end of 2019. We looked specifically at the Gremlin metagenome repository and the pConsFam database. When we had a look at these, Gremlin seemed to have slightly higher quality models, but they only had predictions for 614 PFAM families, whereas pConsFam had generally lower quality predictions than Gremlin, but they have some 13,000 more predictions. At the bottom here, you can also see on the left, this is the model, and on the right, this is the crystal structure, and again, left model and crystal structure. So you can see that both databases are doing a decent job for certain cases. So we had a look at the Gremlin database, and we found that since they made their models, 36 protein families had been experimentally characterized. Of these, we took away 9 because of the models were either just bad or the data was really low resolution, to give 27 test cases. For pConsFam, we found that only 5 of the 27 had decent models, so we supplemented this with 2 other families that were known to have good models. This gave us a database. This gave us a test set which covered a large number of molecules for asymmetric unit, resolutions, residues, and sequence identities. So the Gremlin results were pretty promising. We found that 9 out of 27 succeeded in MR. 8 out of 9 of these required automatic truncation by AMPL to succeed. But when we did this, we found that we could solve up to 3 molecules in the asymmetric unit and resolutions as low as 2.9. It's also worth pointing out on the right that this wasn't limited to one sort of protein type. It wasn't just all alpha helical proteins. It was many different types. Meanwhile, with pConsFam, we found that 4 out of 7 succeeded in MR. All 4 of these required automatic truncation by AMPL to succeed. At times, it required quite significant truncation. On the right, in this case, 5AZB needed to be truncated to about 23% of the original model in order to succeed. But this, again, was quite promising. It solved models with 27 or as low as 27% sequence identity to the model protein. Now, that research was done at the end of 2019, and as the last talk has shown, in silico modeling has continued to improve massively. In Cas14, AlphaFold 2 has been lauded as having solved protein folding. Now, whether they've done that completely, I don't know, but at least as far as Cas14 was concerned, they absolutely smashed it. On the right here, you can actually, here's one of their nice figures they've made comparing their experimental results, their computational predictions to the experimental results, and you can see that it's almost spot on. We did AMPL runs on all of these just as part of the assessment and found that 27 out of 31 models were able to succeed using, well, I say succeed, they were able to be placed correctly using phase MR. Of these, only 3 actually required truncation to succeed, although a modest truncation, say cutting 5 to 10% off of it, where there are more errors, did improve the stats for the majority of cases. Okay, so in these 3 cases where truncation was needed, in this figure I'm showing at the top the full AlphaFold 2 models. They're colored on a scale of blue to red, where red shows more error. At the bottom, I'm showing the truncated AMPL models. So on the left-hand side here, this is what I would have expected for modeling a few years ago. So what I mean by this is they haven't managed to perfectly nail the entire structure, but they've nailed part of it. So this right-hand region of it looks really good. And as soon as you truncate down to that, it works well, it gets placed fine. The middle structure is, I think it's just, it should be a really difficult case. It's a dimer. It's got domains that are just linked together. And the way that these domains are placed is kind of reliant on the other molecule in the dimer. So the fact that they've managed to model the individual domains really well means that as soon as you cut down to a single domain, that works and that can be placed correctly. Finally, this case kind of encapsulates AlphaFold 2's modeling results. You can see that this is almost identical to the crystal structure, but there were two little spots with errors in them. And as soon as we cut those off, it worked perfectly. And it turned out that those were just interfering with crystal packing. So perhaps the wild type would have had that. It's just a crystal remnant. Now, onto the second part of this. How can we make these models accessible for MR? Well, to temper hopes about AlphaFold a little bit, those models aren't really available yet. But maybe to answer the question from the last talk, I do think that other groups are now sort of catching up with AlphaFold. So I would say the groups that came in second at this CASP 14 were probably on a par with AlphaFold at the CASP before. So hopefully in the next few years, other groups will catch up and we're going to have wonderful models across the board. And once those become available, we want to be able to access them and use them in MR. So currently we're developing MrParse to include a second table, which contains models from online databases and information about those models. So let's just zoom in on that table. This is going to contain information about where you can access the model, who provided it, the date that it was created, the sequence and coverage, and then a model quality assessment score, in this case Q-mean. Then also a visualization about the region that it's covering. This currently is a mock-up, hence why there are only 2 models in it, because it took a long time to collect all this information together. It's only got 2 in it. Because of it took such a long time, I was reluctant to do the second. But we are currently developing a mode to sort of get this done automatically. And this will be using 3D Beacons API. So I want to thank Samir because we had a chat at last year's study weekend and he introduced us to 3D Beacons. This is just a slide of text that I've taken from their community proposal. I'm not going to read this, but to summarize, what they're trying to do is create an API that will access lots of different databases of models and allow you to access them more easily. So this is perfect. This is exactly what we want to do. The way it works is that each of the databases has to set up a beacon. The beacon will communicate with the beacons network. So if you imagine me on my computer running MrParse, I'll input a sequence, I'll send that to the beacons network. They'll send that to each of the beacons and they'll say, hey, we have the sequence, what do you have that corresponds with it? If they have anything, they send this back to the beacons network, and that gets compiled into a list of models and metadata about the models, such as when they were made. Currently, this is in prototype stage, so they've got it set up with beacons for the PDBE, Swiss model, and Genome 3D. They plan to set it up with Gremlin and Modbase, and then it's likely that this will expand to other groups because groups who make these models really want to disseminate the models and have people use them. This is likely to be available, the early prototype, by the end of February this year. So you can imagine that it will get into MrParse very soon after. And then hopefully more groups will be added to this and it will become a much more useful tool. So to conclude my talk, MrParse collects information about your reflection data and sequence in one place. Predictions about secondary structure, coiled-coil, and transmembrane are then mapped onto the sequence, which can help to inform your strategy for MR and crystallography. And indeed, a lot of this is transferable. You could also use it to try and find a model for map fitting in cryo-EM. In the near future, in silico predictions will be displayed by MrParse using the 3D Beacons API. And we're going to upgrade the CCP4 I2 interface as well as making this available in CCP4 Cloud. So some quick acknowledgements. I want to thank Jens Thomas, who did the majority of the programming on this before he's moved on to, well, quite literally greener pastures. And then Dan Rigdon and Ronan Keegan, who came up with the idea for MrParse and sort of directed it. But without further ado, that's me.